Very good evening, one and all. Welcome to the revision series for university exams and our subject, digital electronics. So we had few of our earlier sessions on number systems, then we had complements, then last session we had Hamming codes. Today, in this particular session, we are going to learn two interesting topics, namely So in this today's session, we will be talking about two interesting topics, namely, number one, Boolean algebra, and number two, we'll talk about canonical and standard forms. Along with these two topics, we also discuss about binary, storage, and registers. So hope we are ready for the session. Right. Welcome. And let's start our first topic, Boolean algebra. Now let me try to understand from you people an interesting factor. What is this? Do we want simplicity, or what we say is miniaturization of your devices? What are you talking all about, sir? Simple, dear. I want something like a small device which can perform more functions but with minimum size and minimum components. Is this really possible? Yes. We can minimize our circuit size and design. We can reduce our number of components. We can reduce the space occupied by your device by implementing an interesting concept called Boolean algebra. So this is a practical importance of learning this concept, and industries, we use this concept to reduce the complexity, to improve the simplicity of the circuit, and to implement more functionalities. So let's have a quick look on this Boolean algebra. So Boolean algebra is started all about in 1854, and we had a mathematician called George Boole who has developed this algebraic system called Boolean algebra. And what is the purpose of, and let me define it. Boolean algebra is a type of algebra which performs binary operations on variables. Wait for a second. What are these two terms? What do you mean by variable? What do you mean by operations? And what are we talking about? Let me just give a hint. So in our earlier sessions, we were simply talking about some of the basic logic gates. So what are those basic logic gates we discussed? AND gate, which is talking about the output of two inputs is high when only all inputs are high, right? So what do you mean by this? So if you want to represent it in form of truth table, if you have two inputs, A and B, we call these two inputs as variables, and the operation AND between these two variables is called binary operation. So today what we are going to talk about Boolean algebra is talking about different variables and the operation implemented on those variables. Now let's have a look. If both inputs are low, we know that A AND with B is 0. Even if one input is also low, the output is low. But when is your AND gate output is high? When both your inputs are high. So A AND with B will be high when both inputs are high. So I just want to connect. These two terms are called as variables, and this AND symbol which we are indicating here represents the operation executed on the variable. And along with this AND gate, we also try to use two important gates. One is OR gate, and another important gate is NOT gate. So what do you mean by OR gate? Even if one input is high, output is high, and if all inputs are low, output is low. Sir, why we are repeating this? Because today in our discussion, we are going to use a number of times this three logic gates. So A OR with B, if both inputs are low, output is low. If even one input is high, the output is going to be high. So OR gate is one important gate, AND gate which we have already seen is another important gate, and NOT gate is also one more important with a single input terminal. What do you mean by this, sir? Here we don't have two or more variables. We have a single input variable and your output Y is simply the complement of it. When your input is 0, your output is 1. Input is 1, output is 0. So we have three important logic gates which we are going to use in our entire discussion. So I wish everyone remember these logic gates so that your rest of concepts will be very easy. Right. So as I told you in the beginning, why to learn all this? Sir, already we have been learning number of things. Why do we implement Boolean algebra and its concepts in digital electronics? Simple, dear. Remember one point, reduce the complexity, reduce the size of circuit, reduce your cost, and more importantly, make your device smart. How comfortable are we to carry our old phones, which are of a big size, with a big antenna? Now you find not only smartphones, even folded phones. All these are possible because of this kind of implementation in the real-time industry. And same example reference we can connect with your first generation computers, which were of room size. Today they have been converted to pocket size. And all this is because of miniaturization, which is nothing but reduction of complex circuit to a simple circuit. So we'll learn about Boolean algebra and how it is contributing to this particular minimization of circuits. Right. So before we talk about different things, let me introduce one important terminology called axioms. Axioms or postulates. Let me just try to get back to a small popular film idea or film dialogue. Adante follow ayipavali. There is a popular dialogue. What it means? So there is no certain things like laws or guidance. It's a belief. It's something like we should adopt it without any proofs. So the concepts which we adapt or the ones which we practice without proofs, you call them as axioms and postulates. Let us look at some of the popular axiom postulates which we are using in our Boolean algebra. So when we start discussing the concepts, the students in the session feel like they are getting back to their school days. Let's have a journey back. We'll start our discussion with first property called closure property. Now what does this particular closure property says? I have variables, I have certain operations. For instance, my input variables are A and B, and I am applying certain binary operation called sum. So if A and B belongs to a natural number n, the sum of these two numbers A plus B should also belong to n. Then we refer it as a closure property. Sounds clear? If A and B belongs to n, the sum of those two numbers should also belong to n. We refer it as closure property. Then the second important property is called as commutative property. I'll give you a pause. Shall we recollect something in our olden days? What do you mean by commutative property? Simple, dear. You have two input variables, A and B, and you need to find out what is its commutative property. Got it in your mind? Don't worry if you are maybe not able to recollect. If your A and B are two input variables, commutative property says that A into B is same as B into A. What is this? Simple. Take A equal to 2, B equal to 3. 2 into 3 equal to 3 into 2, right? Similarly, in your Boolean algebra also, if A star B is also equal to B star A. This is called commutative property. And the third property which we have is associative law. So for associative law, we will go ahead with minimum of 3 variables. And what is the associative law states that if you A, B, C are 3 different elements, first you calculate the product of B and C and then multiply with A. The result will be same when you first multiply A and B, then multiply with C. This property is called associative law. So these 3 are the first 3 fundamental postulates which we are using in our Boolean algebra. Sounds clear? Good. So next, we go ahead with identity element. What is this identity element? What is its necessity? Simple. An identity element is something like, if I am X, then what should I multiply so that I get back my X itself? In our simple multiplication, if my number is 5, with which number should I multiply so that I get 5 itself? 5 into dash equal to 5. So what is the dash value? Simple it is 1. Similarly, in your Boolean algebra, you have an variable X and you have an element called E. When you multiply E with X or X with E, it again results in X. Then E is called as identity element. Sounds clear? Right. And next we have something called inverse of a variable. What is this? I am Mr. 5. What should be my inverse so that I become equal to 1? It's a simple. 5 into dash equal to 1. What is that dash value? Simple. It should be, the dash need to be 1 by 5 so that when I multiply 5 with 1 by 5, it is equal to 1. Here 5 is nothing but my X. And what should I multiply with my X so that the product of this two is equal to identity element E. So this particular Y function which you multiply with X so that the product becomes an identity E, you call it as inverse of, Y is called inverse of X. And then we have distributive law. Please try to remember this because this is one of the very important laws which we are going to use in different Boolean theorems, particularly in specific called as De Morgan's theorems. Okay? So I wish everyone remember this. And what is this distributive law? For instance, I am trying to multiply X with Y and Z. So that will be distributed as X star of Y and then and X star of Z. This property is called distributive law. Let me quickly recollect what are the different axioms we discussed. We started with first closure property, commutative property, associative law, and then we discussed identity element, then inverse, finally distributive law. These are the 6 different axioms which we have, which we need to remember to use these particular postulates in your different Boolean theorems. So shall we proceed for the next? Right. So please try to remember this because the next topics are dependent on this particular postulates. Right. So in quick, in case of our exact Boolean theorem or Boolean algebra, what we need to mention. So for closure property, we are talking that the structure is closed with respect to operator plus in Boolean theorem indicates or, and dot in Boolean theorem applies for and. So your structure is closed with respect to or and operations, and then your identity element. If I am a variable X, what should I do? I should add to X so that it remains X itself. So for additive nature, X should be added with dash so that it remains at X. The answer is simple, it is 0. In the same X, if you have to AND with a variable so that your result is X, and that dash is equal to 1. So 0 for OR operation and 1 for AND operation are called as identity elements. Sounds clear? Right. Then what is our commutative property? Earlier we just solved X star Y equal to Y star X. Similarly here, X OR with Y should be equal to Y OR with X. Similarly, X AND with Y must be equal to Y AND with X. These two properties are called commutative property with respect to Boolean theorems. And coming to your distributive property, X AND with Y OR with Z. So first we are starting with and inside the bracket you have OR. Now when you apply this distributive property, now X AND with Y and OR will be in between and X AND with Z. Similarly you have X OR with Y AND with Z becomes XOR with Y and XOR with Z. Remember, these particular properties which you are seeing on the display is very, very important when you try to simplify your Boolean expressions. Sounds clear? And last, we have an element B which belongs to, or X belongs to B such a way that X plus X complement. So what do you mean by this? So just like we have talked about our inverse elements, we have an element for X called as X complement. When you do the sum of this, it is equal to 1. And when you do the product of these two variables, variable with its complement, the product or AND gate resultant is 0. So this is a very, very, very important property which we have to remember. So please remember, X OR with X complement equal to 1 and X AND with X complement equal to 0. So these two are very, very important properties. So please do remember, we are going to use them number of times during this session. Right. Now, a minute of pause, because the one which we are going to learn next is very, very important. Why it is important and how it is helping in our reduction or simplification of circuit. Let's look at it. Duality. What is the spell? Duality of your Boolean algebra. Okay, so duality principle states that, in simple, for every algebraic expression which we have been seeing here, we have a set of binary operators, and when you are interchanging those binary operators and identity elements, then we will get the duality. Sir, a bit confusion. So every algebraic expression postulates binary operators. Let me do it simple here. What is that? So here you have your binary operators AND, comma, OR. And next, your identity elements are 0 and 1. So AND operation and OR are called as operators, and 0 and 1 are called as identity elements. Now, what do you mean by duality? Sounds clear? What do you mean by duality? Look at the board. First, if you have an expression X OR with 1 is equal to 1. If this is one of my theorems or postulates. For this expression, I need a duality. What do you mean by duality here? As mentioned, so what we are, your binary operators and identity elements are interchanged. So what's our binary operator here? OR. So we have to replace our binary operator with the alternate, and your identity element 1 need to be replaced with, yes, X OR with 1, and X AND with 0 is equal to 0. What is the reason? Here the identity elements are 1 and 0. 1 will be replaced with 0 and OR will be replaced with AND. Sounds clear? This is a duality principle, and we will work out on number of examples so that we get a better understanding, because that can be used. So duality of expression is obtained by interchanging your OR and ON and AND operators, and also replace ones with zeros and zeros with ones. Sounds clear? A duality principle is obtained by interchanging OR with AND with OR, and also 0 with 1 and 1 with 0. Okay? So, let me try with some examples. Clear? We'll try this. No issue. First, we'll take something like X plus or XOR with X complement. We just discussed when you do the OR operation of a variable with its complement, the resultant is 1. You want to prove it. Okay. if x equal to 0, what is x complement? It's simple. Complement is reverse of your x. In same way, if x equal to 1, your x complement will be 0. In both the cases, when at least one input is high, the OR gate, the output is equal to 1. Sounds clear? Good. Then, what will be the duality of this particular expression? What is that? First, your OR gate has to be interchanged with and your variables remain same, and your identity elements has to be replaced. That is 0 becomes 1 and 1 becomes 0. So want to check it. If x equal to 0, x complement is 1. If x equal to 1, x complement is 0. In either case, if at least one input is low for AND gate, the output is 0. So duality of a function is obtained by interchanging OR with AND with OR. At the same time, identity elements, 1 will be interchanged with 0 and 0 will be interchanged with 1. Sounds clear? This is a very important concept because we have straightforward questions in your university exams where a function is given and we are asked to determine the duality of that function. Right? Sounds good? Right. Now, based on application of what you have learned. Sir, what's that? So, we are trying to connect with what all the discussion that we had so far in terms of various Boolean theorems and postulates. Let me once again try to connect you or remember axioms or postulates of a Boolean algebra are those which we have to accept without the proof. And your theorems are based on those postulates. Sounds clear? Postulates are the ones which we have to accept without a much proof, and theorems are the ones which are based on your postulates, and using these postulates and your theorems, we are going to simplify your Boolean expressions. Now let's start with first postulate. I think we have just discussed already x OR with 0. X OR with 0, it's a simple. For instance, we'll take this x OR with 0 and your x can be 0 or 1. For instance, I go ahead with x equal to 0. Then 0 OR with 0 is 0. And if x equal to 1, 1 OR with 0 is 1. So your output is same as your x value. So what we can mention, x OR with 0 equal to x. Clear with this? Now, the duality of this expression is very simple. What is that? Number one, try to replace your binary operator with AND with OR. So here x OR with 0 is replaced as x AND with, and 0 will be replaced with identity element 1. So x OR with 0 equal to x is your first postulate number 2. And here the duality of that particular one is x AND with 1 equal to x. Sounds clear? Duality, OR interchange with AND interchange with OR, and identity element 0 interchanged with 1, and 1 will be interchanged with zeros. Clear? This is very important one because we have to use this in our simplification of various Boolean functions. Now, next postulate which we have is a variable. Just now earlier we discussed that a variable when it OR with its complement, if 0 OR with 1 or 1 OR with 0 is equal to 1. So a variable when it is OR with its complement, it is always equal to 1. This is your postulate number 5. And what will be the duality of this? The OR gate becomes AND gate and your identity element 1 becomes 0. So the duality of this expression is x or become and with x complement, and identity element 1 becomes 0. That's it. So this is your second postulate, and based on this we want to prove a theorem number 1, x OR with x. So when you are trying to OR a variable with variable itself, that results in x. We will be looking all the proofs of the theorems in the next slides, but let us try to remember x or a variable OR with variable is the variable itself, and that variable we are talking it as variable x. Now what will be the duality of this? Let me hide so that you can guess it. Simple. Now OR have to be replaced with AND. So what is the duality expression of this? X AND with x is equal to x. This is your theorem number 1. And second theorem is, we already just tried to prove it earlier, that when you are trying to, give me a second, x OR with 1, whether your x is 0 or 1, when you OR with 1, you are going to get it as 1 itself. And duality of this, a variable x OR becomes and 1 becomes 0. So x AND with 0 is 0. This is theorem number 2. Next, theorem number 3 is involution. Now let me look at a smart example to make you understand what is this particular example. What you are mentioning, x complement whole complement is equal to x. Can we prove it, sir? Let me try. Let me take x equal to 0. What is our x complement? It is equal to 1. Once again, if I take the complement of this, then 1 complement is equal to 0, which is same as x. So what we can prove now? That x complement whole complement is equal to x, and this theorem is called your involution theorem. Remember, this is also one of the popularly used particular theorem in our simplifications. The next one is your postulate, which is commutative. Number of times we already discussed. What is a commutative property? X OR with y will be same as y OR with x. And this, if you are trying to apply the duality of it, the OR becomes AND. So x AND with y is same as y AND with x. Sounds clear? Great. Then associative law, this is also what we have learned, that is x OR with y OR with z. What do you mean by this? Sir, you have 3 different variables. What do you mean by x OR with y OR with z? First calculate y OR with z. Whatever the resultant you get, then you OR it with x. For instance, I take right. So let's take this simple example. X is 0, y is 1, z is 1. Right? Now, first we apply this x OR with, that is 0, OR with, in bracket value is y OR with z. What is your y? Y equal to 1, OR with 1. And we know from your OR truth table, 1 OR with 1 equal to 1. So this is clear, right? Now let's prove this. The second part, in your school days we used to mention LHS equal to RHS. Now we have already taken our LHS. Now let's prove our RHS here. Now what's our x? X is 0, OR with 1. And then we'll OR with 1. So 0 OR with 1, from our OR gate, we know that it is 1, and 1 OR with 1 is always 1. So your LHS is 1 and your RHS is 1, hence your X OR with Y OR with Z is equal to X OR with Y or with Z. And what will be the duality of this? Only one concept here. OR becomes AND becomes OR. Identity element 0 become 1, 1 becomes 0. So X OR with becomes X AND with, Y OR with Z becomes Y AND with Z. So this is your associative law. Then we have a postulate called distributive law. This we have discussed earlier in our postulates. What is it mentioning about? So let me just what's our postulate? Distributive X AND with Y or with Z. Distributive law means here AND is common to both the variables. So what we'll do here? X AND with Y, and here Y and Z have that OR operation. Now that will be here. Next you have X AND with Z. This particular property is called as distributive law, or you're also mentioning it as postulative 4. Then the most important theorem. From exam point of view, you have a number of times this particular question repeated. State and prove De Morgan's law. So I have this discussion in our next slides. So remember, what is your De Morgan's law? A variables OR X OR with Y whole complement. First you are calculating the OR operations of the variables, and then you are trying to take the complement of that, then that is equal to individual variable complements and with their respective complements. So X OR with Y whole complement is equal to X complement and with Y complement. What will be the dual of this? X OR with Y become X and with Y whole complement. Here X complement and with Y complement becomes X complement or with Y complement. This particular property is called De Morgan's theorem. Very important for your simplification as well as for your university exams. And your last theorem is absorption. What is this absorption, sir? Look at your expression. X OR with XY. How many variables were there? We have initially two input variables X and Y, but your output you have only one variable, whereas your other variable Y is observed. For that reason you call it as absorption theorem. So X OR with XY is nothing but X, and its duality is X and with X or Y equal to X. So these are the different postulates which are used for proving different theorems, and these are your 6 different Boolean theorems which we have to remember, and sometimes we will be asked to prove those particular theorems. Let me start with some of your important theorems. Now first theorem is X OR with X is equal to X. Remember, for theorems you can use your postulates as a one method, or another method is using your truth table. Let me first try to use our postulates which we have learned so far in our discussion. What is that, sir? X OR with X is equal to X. Now I want to write, I have one of our postulate and theorem that X and with 1 is equal to X itself. So I can write X plus X as X plus X and with 1. Okay. So we started with our LHS. Give me a second. Okay. So LHS side. And we have one of the very important theorem that a variable OR with its complement is equal to 1. So I want to replace 1 with x or with x complement, and now let me try to do some products. X and with x plus x and with x complement plus x and with x plus x and with x complement. Now previously we have seen a variable when it is and with itself, it is resulting in the variable itself. So I have a doubt. If x equal to 0, 0 and with 0 is 0, 1 and with 1 is 1, and similarly x and with x complement, if 0 and with 1 or 1 and with 0 is 0. So here you will be left out, and also one more important thing, x and with x is equal to x. So let me replace 0, x, 0, and once again one more important postulate and theorem, that is a variable or with itself. For instance, x equal to 0, 0 or with 0 is 0, 1 or with 1 is 1. So what we can say, x or with x equal to x. So your final expression is x. So you started with LHS, used your identity laws, then you used some more additional postulates. Finally you proved that this particular LHS is equal to your required RHS. Now coming to your the B expression, very simple. What are you doing all about? Boss, let me look at duality principle. What's my duality principle? Replace or with and since you are not using any identity element, simply I can say x and with x equal to x itself. If x equal to 0, 0 and with 0 equal to 0. If x equal to 1, 1 and with 1 equal to 1. So this is your first theorem and the respective proof. Let's go for the next. Your second theorem, x or with 1 equal to 1. I want to simplify your things. We have a long procedures, but let me take a simple proof. What is that? If your x equal to 0, what is your expression for this? X or with 1, 0 or with 1 equal to 1. If your x equal to 1, 1 or with 1, again, even if one input is high, your OR gate is 1. Sounds clear? If you want something more, we can once again go ahead with a different calculation. X OR with 1 is x OR with 1 into 1 and then do the simplification. But this is sufficient. Now when you apply the duality of this, what do you get? X and with 1 becomes 0 and x and with 0 is 0. This is your second theorem. Then third theorem, which we have already proved, that is x complement whole complement equal to x itself. We will be using this number of times. A variable's complement, whole complement is same as the variable itself. X equal to 1, 1 complement, whole complement. First, what is 1 complement? 0. And once again, 0 complement is 1. So where we started and where we ended, it is same. Sounds clear? This is called theorem number 3. And then we'll proceed to theorem number 4, which is your, remember, what is this? This is your distributive property. X or with y or with z is same as x or with y or with z. Sir, what are the different ways to prove it? Simple. You have to take a truth table. My goodness, sir, you have to do a long work. No problem, we'll do it. Then we'll calculate x or with y or with z. Remember, when you have 3 inputs, you are going to have 8 combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1 0 1, 1 1 0 and 1 1 1. Right? Okay. So, when you try to first calculate y OR with 0, 0 OR with 0 is 0, 0 OR with 1 is 1, 1 OR with 0 is 1, 1 OR with 1 is 1, 0 OR with 0 is 0, 0 OR with 1 is 1, 1 OR with 0 is 1, and 1 OR with 1 is 1. So you have y OR with z value to which you have to OR with x. That will be 0 OR with 0, 0, 0 OR with 1, 1, then 0 OR with 1, 1, 0 OR with 1, 1, 1 OR with 0, 1, 1, 1, 1, 1, 1, 1, and same 1, 1, 1. Now if you repeat the similar calculation for x OR with y followed by z, you will be getting the similar functions. For instance, I calculate x OR with y, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1. And you try to do the OR operation, so whatever you are going to get here is same as what you got in this particular column, right? So we can say that x OR with y OR with z is equal to x OR y OR with z. This is your associative property. Now same with next one, which is a dual expression, OR becomes and you are going to get your respective things. Then you have De Morgan's law. As I said you, this is the most important theorem which you have. So what you have to do is, we are going to take x, we are going to take y, then calculate x OR with y and x OR with y whole complement. Similarly, you have to calculate x complement, y complement, and finally the AND of x complement and y complement. Sir, last time you have shown 8 rows, but this time you will have only 2 inputs, 4 rows. 0, 0, 0, 1, 1, 0, 1. What is the R of this? 0, 1, 1, 1. So what is x plus y whole complement? Complement of this, that is 1, 0, 0, 0. So if your x is 0, 0, 1, 1, x complement is 1, 1, 0, 0. If your y is 0, 1, 0, 1, y complement is 1, 0, 1, 0. And you do the AND of this two, 1, 0, 0, 0. The reason is, for AND gate, your all inputs should be high, else it will be low. So what we could observe, x plus y whole complement is same as x complement and with y complement. Maximum of examinations you find this question with the required proof. And duality of this, OR becomes AND. So x AND with y whole complement. So x complement AND becomes OR. Or you have to use the similar truth table and try to calculate the values. Okay? Right. The absorption theorem, the last theorem. But remember, in our exams, they generally try to give an expression, ask you to prove that particular theorem. So here, in the absorption theorem, we start with 2 variables, x OR with xy. Now in this 2, what is common? We find x as common, so 1 OR with y. So what happens here? 1 OR with anything is 1 itself, and when you do an AND operation of 1 with any variable, that is equal to the variable itself. So out of, you started with 2, you ended with 1 variable, so you have observed a variable y. This is called absorption. And what will be the dual expression? OR becomes and your AND operation becomes OR. So these are the 6 different theorems and the postulates which are very much useful in your Boolean algebra. Now, there is one more very important theorem which has been frequently asked in your previous year's question papers. Let's look at it. What is that? This particular theorem is called as consensus theorem. What is this? Consensus theorem. Now, what do you have to observe here is, first, you have three variables, x, y, z, and first x you are having with y, and you have z with x complement, and your third variable is without x, that is y and z. Now, if you simplify in your output, you are missing this third variable. Surprised? What to do to get this? Simple, boss. Xy plus x complement z plus yz. I don't want x to miss here. I'm a fan of x. But in this expression, in this particular term, x is missing. So let me do something which we have learned. My missing term I replace with 1, and we know what's our missing term? X. So 1 can be replaced as x plus or x or with x complement. Now you have xy plus x complement z plus xyz plus x complement yz. So you have a common terms. Take xy as common between these two. So you have 1 or with z, and then you have x complement z. You have y plus your 1. So what happens is this terms x, and we are left out with x complement z, which is your right hand side. So we started with 3 terms, but we ended with 2 terms. This is a question which was asked for 6 marks in a recent university exam. So you have to prove this, but all this was possible only when we know our postulates and theorems, and we know which theorem or which postulate to be applied to get your simplification. And when you know this, the duality is replace or with and with ors, you are able to get your duality expression. And next, this is one more 4 marks question. You are given a particular function and you have asked to calculate duality of it, and believe it, you got it for 5 marks. Sounds awesome, right? So what we learned in this 40 minutes, giving you 5 plus 5, 10 marks. How do we get a dual? Sir, you are repeating this mantra. What is that? Replace and with or with and, 0 with 1, and 1 with 0. So duality of f is obtained by replacing or with and. B, once again, or with and this is an and term. Now you have to replace with or terms. So what you need to do? Complete this multiplication. A and with B plus A and with B complement plus A and with B and with C complement. So A and with A is nothing but A itself. You get A and with B, and B and with B complement. A variable with its complement is 0, and you are left out with AB, C complement. Take a common of AB. We get it as 1 or with C complement. We know anything or with 1 is 1. So we are left out with AB and with 1. So this is one of the best examples that we are reducing your number of terms. So how do we get your duality? Simple. Remember this mantra which we are mentioning for last 40 minutes and try to simplify it. You're going to get your dual expression. Clear with this? Great. Now, there are 4 different particular operators which we have mentioned in this discussion. The first one is about L variables which you have in parenthesis. Then you have complement, then and operator, and finally or operator. So whenever your expression is having like this, what is that? Something inside a parenthesis followed by complement and then outside you have and finally some OR operation. So what is this operator precedence? First, calculate what you have in the parenthesis, number 1, then your complement, then number 3 is your and finally your OR. Sounds clear? So this is called operator precedence, which you have to follow when you are implementing simplification of Boolean functions. Right. So this is your first topic. Now the second one is a simplification or extension of that, but we have to be a bit careful, which is canonical forms and standard forms. Now so far we were talking about variables in isolated. Ante enti sir? Simple. What is that? I have a variable like x, or I have a variable like x comp. But now what I am trying to do is I want to take these different variables and apply them to an AND gate. For instance, I have, let me take instead of x complement, this is y complement. So my term, which is AND product of x and y complement, that is x and with y complement, this is called a canonical minimum term. So what do you mean by canonical term? So when you are trying to get product of more than one variable. So in this particular first case called canonical minimum term, a normal variable, for instance a and a complement, a normal variable is indicated with 1 and a complement of the variable is indicated with 0. So please try to remember this, a normal variable with 1, the complement of it with 0. So minimum terms are 2 or more, give me a second. Minimum terms are 2 or more binary variables combined with AND operation, as I told you just now, x AND with y complement, and then they are referred as minimum terms or standard products. We have difference between canonical and standard, which we'll try to discuss, but remember minimum terms are variables which are applied to AND gate. They are product terms. Clear? And then this is a simple example. Remember, in your minimum terms, complement variables are indicated with zeros, normal variables are indicated with ones. So here I have a function or a particular minimum term with x complement, y, z complement. So x is in terms of complement 0, y is in terms of normal variable 1, z in terms of complement. So 0, 1, 0 if you are converted, that is nothing but 2. So a minimum term is indicated with a small letter small m, and that equivalent value is indicated as prefix. Clear with it? Right. For n variables, you are able to form 2 power n minus 1. So same with other format, which is called maximum terms. Now let me tell you, there you are using AND gate and trying to calculate product. Here we are using an OR gate and we are calculating the sum. So you may have two different variables which are applied to OR gate. This is your sum term. Okay? And you call this sum terms as maximum terms. But there is a small difference between minimum and maximum. Here, a complement term is represented with 1 and normal variable is represented with 0, exactly vice versa of your minimum terms. So if you take an example, what is this? So in maximum term, normal variable is 0 and complement is with 1. So here x complement or with y or with z complement, complement is indicated with 1, normal with 0 and again 1. And maximum terms are indicated with capital letter M, and that here this indicates that binary decimal equivalent of those 1, 0, 1. This is canonical forms, minimum terms and maximum terms. Okay, as I told you, right now x, y, z, how many variables we used? 3 variables. Whenever you are using 3 variables, you are going to get 8 combinations because 2 to the power of 3, and your value starts from 0 and ends with 2 power n minus 1. So for 8, 2 to the power of n minus 1 is nothing but 2 cube minus 1, 7. So you have 0, 0, 0, 2, 1, 1, 1, 7. Let me take one simple example to understand how to represent the variables in terms of minimum terms and maximum terms. Let's go with a favorite one. Okay, we'll go with 0, 1, 1. This is our reference. I want to express 0, 1, 1 in minimum terms. In minimum, 0 indicate complement, 1 indicate normal. And 0, 1, 1 are representing x, y, z. So minimum term 0, 1, 1 is nothing but x is 0, x complement, y equal to 1, y, and z equal to 1. But same in terms of maximum, 0 is indicated with normal and complement variable is indicated with 1. So 0, 1, 1 becomes x or with y complement or with z complement, and maximum terms are indicated with capital M, minimum terms are indicated with small m. So this is important. So here we are using in terms of product terms, these are in terms of sum terms. Product terms, sum terms. Okay. Now, and sum of products. So here we have this next representation where instead of one term, we are calculating multiple terms. So first you are calculating products, product 1, product 2, then you are calculating sum of it. So you call it as sum of products. Whereas for your maximum terms, first you calculate sum and then you calculate the product of those sums. For that reason you call this maximum terms as product of sums. Sum of products is sum of different product terms, whereas product of sum, first we calculate sum and then we calculate the product of it. Sounds clear? This is SOP and POS, which are also called minimum terms and maximum terms. Okay. So we have few 2 minutes, somewhere around in 10 minutes we'll try to conclude our discussion. Please try to stay back and try to get your maximum input. Okay. Now in SOP we just mentioned about it. So we have certain terms which are included whose value is 1 in your Boolean function, and that we have to represent. Now what is this? And let me try to show you. So look at function 1. I want to express sum of products. Let us take function f1. From your truth table, find out what are the combinations of x, y, z for which f1 equal to 1. What are that? 0, 0, 1, then 1, 0, 0 and 1, 1, 1. So in your SOP, 1 indicates normal, 0 indicates complement. So 0, 0, 1 is nothing but x complement, y complement, z. 1, 0, 0, x, y complement, z complement, and next 1, 1, 1, x, y, z. So my f is a function f is sum of products. What is indicated for sum? Sigma. Minimum terms are indicated with small m, and what are the sum product terms for which function equal to 1? What are that? One is 0, 0, 1 nothing but 1, 1, 0, 0 is nothing but 4, and 1, 1, 1 is nothing but 7. Now I have a bit of twist. Surprised? Don't worry. If you know f1, what will be the complement of f1? f1 complement is nothing but what all the terms which are missing in your small m or your m. So what are that? we are missing with 0, 2, 3, 5 and 6. So this is called complement of a given function, and let me twist you saying that this is same as your f1 and represented with product of sums, product indicated with pi and maximum terms are indicated with capital M, and you can write this same as f1. So your minimum terms, whatever the terms which are missing in your function, they will be a part of your product of sum representation for that same function. This is a very important one, right? Sounds clear? Now F2, we have 4 different functions. Similar way you have to express what are the values for which F2 equal to 1 in your respective. So F2 is equal to sigma small m. What is this? 0, 1, 1, 3, 1, 0, 1, 5, 1, 1, 0, 6 and 1, 1, 1, 7. Sounds clear? And when you have to represent them in terms of product of sums, what is missing? 0 is missing, 1 is missing, 2 is missing there, or here it is equal to 0, and one more is we have 4. Clear? This is how we are representing our Boolean function in in SOP and POS. Okay? Right. So far our discussion is happening for variables, then we discussed about product term, sum term, then we extended to sum of product and product of sums. So in simple, you started with X, you started with Y variable, then product term is nothing but XY complement. Similarly, X complement Y. These two are individual product terms. After that, we have applied to an OR gate so that you get your output Z. So this Z, which is XY complement plus X complement Y, is called sum of products. The same with product of sums. There you will have initially OR gates, and then first you have OR gates, and then you will apply this OR gates to your AND gate. You call it as first sums, then the product. So that will be referred as product of sums. Now the next very important one is called as standard SOP and standard POS. So what it is and what is its significance, let me try to make you quick understand. If your function, so what is a function? A group of product terms or sum terms. Sometimes what happens is, in your given function where you have a series of terms, every individual product term or sum term should contain all the variables of your function. Simple. Function is a variable of 3 variables. That is, you have 3 different variables. So you will need to have all those 3 variables in each individual product term. That is happening, then your term is standard product of sums. For instance, this is a function of 3 variables. So your first product term, 3 variables. Second product term, 3 variables. Third product term, 3 variables. So all your product terms all have all the 3 variables of your function, then that is called as standard SOP. Similarly, if your all product of sum terms have all the function input function variables, then you call it as standard POS. Now I have left one last very important topic is how to convert your SOP to standard SOP and how to convert POS to standard POS. So first we'll go ahead with conversion of SOP to standard SOP. Already we discussed earlier. For instance, f is function of xyz, but your function is having only yz. Just now, previous reference we referred it. So my favorite x is missing here. So what I have to do? Replace yz as yz into 1 because a variable and with 1 equal to variable itself. In place of 1, replace 1 as the missing variable with its or of its complement. Now what are you going to get? XYZ plus X complement YZ. This is only SOP form. In this, every product term has all your variables of a function. So this is called as standard SOP. How do we convert SOP to standard SOP? We are multiplying with 1 and replace 1 with missing variable or with its complement. Then you are able to complete SOP to standard SOP. Now same way, how to convert POS to standard POS. Now we know what is POS, X, Y, Z. It is having an expression like X plus Y. So what is missing for me here? Z, which is a part of your function, is missing. So what you do is, you write X plus Y as it is, but add a 0. Nothing wrong. A variable or with 0 is variable itself. So once I write that, I use one of our property of identity, that is a variable and with its complement. What's my missing variable? Z, and with its complement. Now I told you, we want to use some important distributive and De Morgan's and all other laws. Using that, this becomes X or with Y or with Z and X or with Y or with Z. Now look at this function. So this is in form of sum terms and we are calculating product, and more importantly, each product term have all your variables which are a part of function. This is called conversion from POS to standard POS. Sounds clear? So what to do? For the missing variable, replace with 0, and 0 have to be replaced with missing variable and with its complement. Then using your distributive law and De Morgan's laws, you try to spread your expression. This converts your expression from POS to standard POS. And look, you get straightforward questions for 5 to 6 marks where you are given a function and you are asked to convert it into different standard formats. For instance, I miss only 1 second, I will take it. If it is AB complement, what is missing here? I miss a variable C. So replace this with 1 and write it as C plus C complement. Similarly, it is AC complement. So what is missing? B. Write it as B plus B complement. For BC, the same. Sounds clear? So you are going to get a questions based on conversions from SOP to standard SOP, POS to standard POS. Very important. And last thing, probably the reason for including this, probably if all the topics so far discussed in our last video and today's video, if we add this, we have been delivered with a complete unit, which can be very helpful for your university exams. So let me tell you, binary, it's simple, 0 or 1. Where to store binary? You call that as a binary cell. It's a place where you store 1 bit of data. The bit can be 0 or 1. A group of binary cells, I have 5 binary cells, so I can store 5 bits of data. So that group of 5 binary cells is called register. And when you are moving your data from one binary cell to other binary cell inside the register, you call it as register transfer. These are some of the very important topics. I believe you people can take maximum advantage, and very hope to meet you very soon in your next topics. Thank you so much.